to Analysis Chat, a bi-weekly discussion with your lecturers for 220. I'm Dr. Biggs, and here with me is Dr. Kikianti.
Hello.
And Dr. Lay.
Hello.
You know, this is our 7th episode.
Mm-hmm.
Semester was 14 weeks.
So it's bi-weekly.
On average, we bi-weekly, I told you. Okay, so our special guest this week is Dr. Maepa.
Hello.
Dr. Maepa's research interests ranges over Banach space geometry, operator spaces, and vector measures. All good topics of analysis. We'll hear a little bit more about this towards the end. He is also the lecturer for WTW 310, the third year analysis course. So I'm sure he'll have some valuable perspectives to share about what comes next in the future of analysis. Okay, so our lectures are just about at an end, or at an end. Mm-hmm. And we've just finished off our last theme of series. So, looking back, what is the most important thing that we want our students to have learned from 220? What do we want them to really take away from this course?
Well, first of all, mathematics is not what you think it is, right?
But that depends on what they think it is.
Because a lot of the students, over the years, I have chat with like a number of students, and there's a good majority who thinks that maths is what you did in calculus, right? It's just questions like evaluate the integral, differentiate the following function, computation.
Yes.
And I even had a student who was so frustrated with 2 to 0, and then he said to me, "This isn't math." I found that really funny because he was like, "No, that isn't math. What you thought was math isn't math."
Well, so, it's the end product of math.
Correct, yeah.
Math builds algorithms.
Yeah.
And those algorithms can then be used for all kinds of useful things.
Yes. So I think just an appreciation as well of, we saw from the beginning, right? We have logical, we studied logic, so we have all these deductions. Mm-hmm. And we start with axiom, and we put the two of them together, and then we get everything that we know about real numbers. Well, most things that we know about real numbers. And this is how abstract mathematics work. You know, it's very delicate, it's very precise. You think about things carefully, and
I think this ties well into what Professor Angelov said last
week. Yes,
right. Is in first year we learn how to use the machine of mathematics to do all kinds of things, but in this course is the first time we learn how to service the machine and how the machine is actually built.
Yes,
and that's what we want. I think our students to get away. Is to have some exposure of, this is how we build mathematics. And at a more fundamental level, this is how to think abstractly.
And learn to reason.
Yes, absolutely.
Very important.
Yes. Yeah. I think all too often we just like, okay, this is the argument as laid out, we churn our machine, we produce it, but we need to actually understand how does the reasoning work? And if we can get our students to walk away with an appreciation for how to reason, I think we've done a good job.
Yeah, I think so too.
As a visitor, I can also make some input here.
Yes, please.
I think there are two additional issues I think they should have learned. One, representations, and the other structure. I think SDiff would be different from calculus. Students, as I call 220, theory of calculus. Mm-hmm. Students should have started seeing some structural precipitation in the different topics. Because in a pure math, we're taking them into structural studies. Vector spaces with their structures, going elegant into algebras, and now you multiply. Going even more now, putting norms, analyticity, interaction of linear algebra, and topology. They should also have realized mathematics is a representation of ideas.
Yes.
So when you say sequence, it's null. In real life, you imagine something out there in the physical world, which is sequential.
Yeah.
Once you say series, you see some compounded evolution of a process over time. So these are the things which ultimately we call education. Remember these bits and pieces of memorized particular things, null sequence, a function which is continuous. For every epsilon there is a delta. It's mechanical.
Yeah.
For every epsilon there is a delta. You can get it right. It's mechanical.
Yeah.
You don't know what it says, but you can solve the problem.
That's the point. In this course, you actually have to start understanding what it says.
Understand, for every epsilon there is a delta. So what should happen in relation to the process in which you want this epsilon to propose the corresponding delta? You know, otherwise it's so mechanical. Then they look at the expression, they do some manipulation until they can chop things so that something is smaller than epsilon when things are close within the prescription of delta, that sort of thing. They may not be very explicit at this stage, but some few students could have started seeing few of them here and there, and therefore asking lecturers, but what does this mean? What do I do with this? What does this mean with closeness actually? When we say for every epsilon there is a delta, what kind of closeness? I can just, for example, equicontinuity is related to continuity in further study 310.
Advertisement.
So you have a group of functions which must be continuous at a point with the uniform epsilon. And then we just say equi, because this epsilon works for all of them. So you see, you take what you know, now you're going to build it further on into particular structural ideas. And that is very useful in studying compactness from phenomena.
No, that is definitely some good basics that we learn in this course. But I mean, those can be picked up. The point is to learn how to reason, I think. And to communicate that reasoning. That's the second part that I think we've put a lot of emphasis on, is you need to communicate your thinking.
I often see students, they actually have the idea, but to write it down they struggle, and this is why we encourage them to do worksheets in the tutorial
and
to practice.
Often I'll just ask them, like, just tell me, how do you do this? And then it's like, if you wrote that down, I would give you full marks, because you've just explained all the ideas required to do this. Yes, you could formalize it a little bit more, but that will come with time. The point is to communicate your thinking.
Yes.
And perhaps this thinking using symbolic language, I think we are not very much into it.
It's abstraction.
We have started allowing them to use it. You know, implies to write the next step. As opposed to by implication, of which you may not know if you can go reverse, and they might have a problem putting it going forward. Think about x is 2, then x squared is 4, but they put in by implication. Going back, x doesn't have to be 2, minus 2. But exactly what we say, logical evolution of thought, based on logic or rules of logic. It's very encouraged.
So, any highlights for the semester?
Any highlights?
The bi-weekly podcast.
The bi-weekly podcast is what it is. Or tri-weekly, or whatever it was.
No, it's bi-weekly.
The podcasts have been really good this year, I think. We have amazing guests. And what else did we do? Well, I really enjoy tutorials, actually, I must say. Tutorials this year, I think we stepped up the challenge to the students, and I like the interaction just when they really sit down and struggle with themselves, and finally, you see that light bulb, and they said, yes, I think I got it. I really enjoy that whenever I see things click in someone, and this, wow, this is really, really nice. Do you don't have any highlights?
Too many to talk.
Too many.
Oh, fantastic. So,
well, one other important highlight is they've been kept very busy.
They've been kept
very busy. So you don't have the time to put the pen in your mouth. Just exaggerated.
Just a bit of background for the students. Dr. Maepa has been monitoring us the whole semester.
That's right,
to make sure that we're taking care of you.
Sometimes you look very close.
That's right. Yes.
I only have one point that for this course, most of the stuff we prove we use real numbers. So what different if we lose the property that the completeness properties? So what left over with the properties that we learned for the whole course?
several areas that we will be seeing in third year is the question, what if we drop this one property? What can we say
what
then?
Can we say then?
So even for the last piece of the team, we're still talking about the real number. And that's not true anymore if we lose one property, the last one. And I hope some students, if they have time for that, they better look at that. If they lose, and sometimes in the proof they don't even talk about that. But it's still like over there. If we lose it, we lose everything.
Yes.
So that is the most important of the service actually. This course we learn how to serve people, but not like we eat the food anymore. So you better try how to cook. If you lose one ingredient, then the food is totally different and you're not gonna get paid.
Wow. So, if you lose one ingredient, you can still eat it. Yes, if you lose one foundational stone here, your whole tower comes crumbling down.
You lose the taste. It tastes differently, probably.
Because the customer is gonna get angry and then you're not gonna get paid. That's really bad. So be careful. So just the reasoning that we already mentioned about, but just see the flow of the knowledge and where it's needed. It's not that easy step, and if we have time, just sit back and enjoy it during the summertime. Not right now because so many courses come to the end. So that's the highlight I think in the course.
So, as we come towards the end, it's maybe a natural thing to ask, well, what comes next for our students? Right? Now, well, quite a few of our students will go on their way. They've had some good fun with us, but they are doing something else than mathematics next year, and that's good, right? We all have to find the thing that we are passionate about and brings us joy. So, for those students, well, we hope they enjoyed their time with us, seeing a little bit how we go about building mathematics. And well, in some sense, we've only really begun to scratch the surface of what is possible to do in mathematics. But so for those who are continuing with mathematics further, well, what will the next year bring? What's going to happen in third year? Maybe we can share one or two highlights for what courses are coming next year.
Well, I think we can start with 310.
Yes, the follow-up analysis goes to 220. That's a good place to start.
Yes, I think students basically have been introduced to concepts. For example, continuity, compactness, and the like.
No, I haven't seen compactness.
Not really compactness. Let me rephrase it. Closed and boundedness. Now, therefore, I have suggested some further elegance. Some further elegance next year would be this closed and bounded is an important property which can hold in a set. In finite dimension. In finite dimension, it implies compactness. Which we're going to stay next year. But you see, in infinite dimension, this is not sufficient. I mean, the compactness doesn't have to imply. I mean, closed and boundedness doesn't have to imply compactness. In infinite dimension.
What is compactness?
So compact. Now another thing.
I have a one that I like.
Here is. Let me tell you that they dealt
What's
with
your story?
They dealt with compactness. Nobody told them. They do it. They said if you have a Bolzano-Weierstrass, sequential Bolzano-Weierstrass theorem, a bounded sequence in R has a convergent subsequence. In a way, it's about a sequential definition of compactness. Because then we have various, in infinite dimensions, we have various formulations.
So it's in trying to generalize some of these ideas.
Exactly. But again, it's because it's an important concept that delivers certain things in structure theory studies. You know, so this is what in 310 you'll be digging deeper. Firstly, we rephrased your concept and we use the word compactness.
But so, also, I mean, we jump from one dimension to arbitrary finite
we go
dimension.
to arbitrary finite dimensions, although the final analysis is in R. Because of coordinates, you know. The finite analysis is in R, so you always have to upload to 3 dimensions to interpret.
So, but speaking of compactness, they also actually saw it although as you said, nobody tell them,
Yeah.
is in 218. When we talk about optimization,
Yes,
when
precisely.
this extreme value theorem
Exactly. Yes.
in Rn still works, right? But what is your reasonable replacement for a closed interval?
Yeah.
There we use a closed set and a bounded set. We didn't tell you.
My
we didn't
favorite
throw compactness
description
there.
of compactness,
Yes.
which is incredibly vague,
Yeah.
is compact sets are sets that act like points.
Compact sets are
Okay, yeah.
well, it's because you have what do you call it? Separability comes in.
Yeah.
You can always take this dense subset. Countable subset. So that's precisely the point. Let me tell you again, the finite dimension is not fair.
Yeah.
Because it hides the concept of completeness.
Yes. That
No
is
one
true.
talked about completeness of a space or of a set. You know, you a Cauchy sequence. You say a Cauchy sequence in R is convergent, but that's because of completeness in R, which is by default.
Yes.
Now, compactness or finite dimensions hide completeness. So you can discuss both the compactness and the completeness together in a finite dimension because they are closely tied together.
Yes.
Now, when you go in arbitrary metric space, so you take your Rn, you put the metric.
Yes.
Now you start distinguishing between the two because in metric spaces, even closed sets can be open. Closed sets can be open. Take the discrete metric. So now they're going to say, what? It's closed and it's open.
Yes.
But if you don't talk the metric language, which we don't do for quite a while until 710.
Another adverb.
So you're not going to realize it, and you think every time we're cheating a bet to make the course relevant. So these are the things you are going to develop in 310. You take what do you think concepts you're familiar with. We go elegant, which means what do you know we show you. You actually scratched on the surface. Let's go deeper. There is a diamond below the surface.
There's a diamond. Yes.
Okay.
Yes, thanks.
But I think we should also let our students know there is mathematics beyond analysis.
That is true. So second year. I wanted to say third year, not second year.
Yes.
There will be a 381, which is algebra.
Yes. Group theory.
Ring theory. Field. You know what field is?
They've seen a field. Ring is somewhat related to that. The group for me is more fun.
Yes.
Because
it's so fundamental.
They've seen some basic objects so far, like a vector space, a field.
Yes.
Group is one of the fundamental objects in mathematics.
Yes. Once you know group, you can write your field axiom in like 3 lines.
Oh yeah. No. Absolutely. It's such a nice object, but I mean, it's also nice and intuitive. If I talk about the group of rotations in space, most students will understand, oh yes, you rotate, and what kind of properties does that group of transformation have? What's at the essence of that? So that's great stuff, and also builds to some very exciting stuff. I get very excited when I talk about groups because my research starts going into that way, where I have groups intersecting with linear algebra, intersecting with analysis and calculus, and they all come together to make this new area.
And measure theory.
Oh yeah.
And then there's a
complex analysis. So some more analysis, but what's the game there? The game is, right, that we actually ask the same questions we ask of real numbers.
But now
but
more complex.
See, can we generalize it when our field is complex? So does it make sense to differentiate? If we have complex functions from complex numbers to complex numbers, can we just use the same definition we had for real numbers? If we do, does something change? Does it just go through? Well, the story is it does change, and it changes in a very exciting way. And leads to beautiful new theory because things are different. And they are different in very interesting ways. Going on with integration, all of that.
You see really beautiful things in complex analysis.
Yes.
It's like you see ugly functions in analysis, but in complex analysis you really see like everything works. Especially once you know what an analytic function is, everything's beautiful and
You also distinguish between, at least it teaches you that.
Yeah.
between a subspace and a subset.
Yes,
There are
yes.
subsets which refuse to be subspaces.
Refuse to be subspace.
For example, take reals as a subset of complex numbers over complexes.
Yeah.
It refuses to be a subspace.
Yes,
Yeah.
yes, yes.
But it's a subset. So one mathematician said the shortest path to the real truth passes through the complex domain.
Well said. Okay, and what else is there?
What is real?
Yes. What is real?
Geometry?
Geometry, yes.
Right.
I've been sitting in geometry this year.
Yes.
So I really enjoy the course. This is where you really get into the axioms. Okay,
Yeah,
so-
I mean, so axiomatic foundations
Yes.
of mathematics, the idea of axioms,
Yes,
right, goes back millennia.
exactly.
And it really started with
Yes.
geometry.
Yeah. So there, you don't have R.
Uh-huh.
So all you have a set of points and a set of lines.
Yeah.
And that's it.
Mhm.
Right? And how are you going to talk about, how do you go about saying a line is shorter than the other line? Because in R, we can measure them. In
Yes.
R2, say, you can measure them.
Yeah.
You can look at their length. So you can say something is shorter than the other
Yes.
one. Now you don't have the notion of length. So how do you do this? What do you mean by a segment is shorter than the other segment? So things like that. And I think geometry really, the way it's presented in this university, I believe if you go to different universities, there's a different way of doing it. But
Yeah.
here it really starts
Wow.
with axiomatic development of it.
I think also at third year level, you start getting some changes in what
Yes.
different universities offer.
Yes, correct.
They'll start offering things that they have expertise
Yes,
in.
yes,
And
yes.
at one university, they might have a topic
Yes.
on geometry. At
Yes.
another university, they
Yeah.
might have a topic that we don't have yet.
Yeah, correct. Yeah.
Precisely.
Yeah.
Yes. Yes.
Then there are other things like financial engineering in
Yeah.
third year.
Dynamical systems,
Yes.
that's beautiful
So
stuff.
That's exciting.
Right?
Yeah.
Looking carefully at differential equations and doing time evolution of various things and
Yeah.
starting to dig into the analysis of all of that.
Yes. And there's partial differential equations.
Yeah.
It's also exciting, I think.
Yes.
Yes. Yes.
Numerical analysis.
Yeah.
Right, where you now.
You know.
I mean, we already mentioned it a little bit in this course.
yeah,
you
actually,
use some
yes.
ideas we've already developed
Yeah.
to actually start challenging yourself
Yeah.
to solve some problems numerically.
We
If you
mentioned-
have a big system of equations,
Yeah.
can you build a sequence which will converge to the solution?
We talked about this during intermediate value theorem, right?
I think so.
Yes.
The bisection
Yeah,
method,
bisection method, yes.
is a basic numerical technique.
Correct, yeah.
So in numerical analysis, that would be a technique.
Yes.
You would show that if you do this algorithm, it's going to converge to
Yeah.
the solution.
Convergence is very important there.
And you will then probably also study how fast does it converge,
yeah.
what kind of errors can occur, what other techniques are there that perform better.
Yeah. So I think they're very important is convergence, right? The notion
Yeah.
of convergence is very important in numerical analysis. And the second one, as you said, is making the error small.
Yes.
And this is
That's-
your
yes,
experience in
yes.
dealing with inequalities will
Yeah.
really be helpful there.
While, of course,
Yeah.
balancing with complexity.
Yes, correct.
It doesn't matter if you have a beautiful algorithm
Correct,
that
yeah.
converges really fast, but each iteration takes a year to compute, then it's useless.
This happens. Anyways. And there's another one, right? Continuum mechanics.
Yes, another slightly more specialized, I think. Right. So, what can we say? Something like fluid motion would fall within the idea of continuum mechanics.
Yeah.
How do we deal with that?
Yeah.
They learn the
Right.
real
What
math.
are the models that we need to? What is the maths we need to develop in order to get to that?
They learn the real math over there.
The real math. You
What is real?
what is real? Yes. Analysis.
Right, and that's only what we have here and now.
Yeah. And
Even
that's only
within-
third year.
Yeah.
Yeah.
Yeah, no. So there's a exciting world of mathematics out there, and you'll probably see that a lot of it only starts happening after you've built your foundations and graduated with a maths degree. Then some topics only start there. They say, okay, well, we need all the stuff you know from your undergrad, even just to start defining the new object we want to talk about.
That's what happened to me, kind of.
I think that's how it happens to many of us.
Yes, yes.
And I mean, in that sense, you don't even know what topic might really capture your passion and joy.
Yeah.
Because you haven't seen it yet. But hopefully it will be mathematics.
Yeah.
Yeah, fall in love for first time. Huh?
Fall in love for the first time. Very sweet.
Yeah, and I mean, this is also not fixed. Many people change. They study something for 10 years and then they change over to something else. Sometimes
Happens.
even into a completely different area, leaving maths or coming to maths.
Yeah, I remember my first boss, I also changed in some sense.
Yeah.
At that point, my PhD was in Banach space theory.
Mm-hmm.
And then I was working in this bioinformatics lab, so it's very measure theory and statistics and all of this. And my boss actually, his PhD was in differential geometry.
Uh-huh.
He completely changed to
Yes.
bioinformatics, and it's fun. And just the experience that you get from learning so much mathematics, I think is very helpful.
Yeah.
I think it's time to also remind our students, right, going forward. It's good to start breaking the barriers, right? Because now you're probably thinking like very compartmentalized. This is linear algebra, this is analysis. I don't like linear algebra, therefore I will do analysis. But guess what? When you're in the 310, you will see that there's some marriage between
some of the
two.
most beautiful things that happen in maths is when one area, like complex analysis, suddenly has major application in a place you would never think, number theory.
Exactly.
And
Number
it's
theory.
Wow.
Number theory these days, they apply techniques from any kinds of mathematics. It's very we had a joke the other day with Professor van der Walt. He said, what do you get if you add 221 with 310? You get 710. Yeah. Essentially, right? This is a linear algebra, and like further analysis. Then you get functional analysis.
Yes.
So
and I mean, I think in our world, as we go further, it's getting much less often that people will study one thing and stick with it. The way the world is changing is most people will likely do several kinds of things in their lifetime and have several careers. And so the important thing is, I think, to learn.
Yeah, learning is very...
learning how to learn.
Yes, learning how to learn. Even
that's
more
the
important.
skill.
Yes,
And by learning, I don't mean memorizing, right? That is... We've got many great resources to help us with memorization now, but really understanding and having new ways of thinking. This is a crucial skill to have, is to be able to adapt.
Yeah.
Okay. But now, speaking of all these exciting different areas that are out there, Dr. Maepa, can you maybe tell us about your exciting research area a little bit? What is it that you look into?
Well, thank you. Banach spaces offer various possibilities in research. By the way, they are linear structures. Banach spaces with norms which are compatible with the structure. But between them you have functions which we call operators. So therefore bounded operators, bounded linear. So one way to understand the structure of the Banach space is through the bounded linear operators between them or on it, like in spectral theory. And the converse is true. To understand properties of operators between classes of spaces, you may have to understand the spaces better. Because what you're going to do, the domains and the ranges of these operators, at the end of the day, they are subspaces of the codomain or the domain. And therefore, if the operator is closed, you want its graph in the domain to be closed. So the properties now go there. So in order to understand it better, you must understand those properties. Now, unfortunately, there are problems which cannot be solved in that which we call category. Category of Banach spaces and bounded linear operators. So what I'm doing is I'm relaxing that. I'm looking at Banach spaces as metric spaces. Metric spaces with the origin pointed. So they are pointed. Therefore, generally, I take a metric space, finite, possibly, even 1 point. But if that 1 point, I can call the point the origin. So I've joined anything I call the origin. So that there is so it's pointed. Then I can look at various classes of those. Compact metric spaces, finite metric spaces of dimension at most 2. That's because of the balls in these guys. The dimensions at most 2. So they respect certain properties of the metric, if you impose that. Then between them, and this is often a mistake, the correct map between metric spaces is not continuous functions. No, continuous functions do not see distances between points. Think about the interval 0, 1, and think about the real line arc.
They're the same.
They're the same. Topology doesn't see. So let's put a bound on the distance. So the Lipschitz map. So Lipschitz maps are the correct morphisms in this new category.
Yes.
So what are we doing? We still studying the Banach spaces in the possibly nonlinear context. And therefore, this framework was started by Lindenstrass, Pelchansky, and the Israeli school and the Polish school, and then it went into the West. So it's a standard today these days. There is a broad literature. Actually, the proponents of the idea, Figel and Ulam in 1932, they come up with a theorem that says, if you have two norm spaces, let's say Banach spaces, and then you have a homomorphism between them, which preserves the origin, then they propose a condition under which would necessitate this homomorphism to be an isometry.
Yes,
that
was just going to say.
That was an astonishment that without even looking for that. So then they ask the question, in a given Banach space, what is the role of the algebraic structure vis-a-vis the metric structure? And they realized the isometric structure is already proposed by the topology. Because this is a homomorphism. And then you already have an isometry. So you can in a way kind of demarcate between the algebraic structure and the geometric structure, which ties into the topology. And it's not surprising because this geometric structure through the norm anyway generates a particular topology. Now, therefore, on this point, on these spaces, there comes all sorts of topologies which you have to interplay in order to arrive at things. The strong one is because of the norm, and the other ones because of what you call the dual. I don't know. These are linear functions on the space into reals, scalars, which are continuous and linear. So, and then you can propose others generated by the space itself. We often call them weak star. And there are many others. If you see these Banach spaces as locally convex spaces, then many others come in various ways, thanks to Grothendieck's representation.
World of fun.
Exactly. So basically what I'm doing, therefore, is to take the problems of Banach space theory in the linear context, which do not have answers, and try and ask them in the Lipschitz category. And because of generalities, of course, with frustrations, differentiability, Gaccio and Frechet, they come in naturally. So if one succeeds in solving it there, then you can always specialize and then you close it. It fits either way. So what you do in there can feed a new outlook on your normal linear structure. So we do not exclude from the pointed metric space the Banach spaces and the linear structure, but we just go bigger. So this is what I'm currently doing.
I think it's just this final point of, we have many functional analysts in the department, right? Many of us. But if you start talking to each one of us, we're all looking at things from different perspective. For example, I see the geometry part, and like Professor van der Walt, for example, he does more like the topology side of it. So this thing that you learn in second year, you learn about vector space, then you impose an algebra structure, you impose another structure, etc., etc. And it's just so good in any of these lessons of learning new structure and how they interact. If you have a really good foundation, right, it's surprising how your first or second year intuition can help you. A very good example I always like is norms, as you said, as a mapping. If it's differentiable, then you try to plot your circle that's the set with norm 1. Smoothness, right, has something to do with differentiability, just like first year. So it's very important, I think, to take these things seriously now, right? Because otherwise you try to build things as complex as Dr. Maepa already explained, right? That everything's gonna crumble. So it's all of these gonna come together, and
Wow.
Students can visit our intranet and just check at my honors project proposal. Not to try and understand.
Another plug.
Another plug.
Just to read and have some idea. And when you are done, come and talk to me.
Can I also plug my note?
We'll make it easy. And then we can see if we can move forward.
You do get that they have to first do third year.
Yeah. One more year.
You advertise too early.
Okay, wow, that has
that-
been quite an enjoyable session.
Yeah.
A nice extra long one for our last one.
Yeah.
Dr. Maepa, thank you very much for joining us. It's been a pleasure.
Thank you. Welcome to 310.
Yay! So that's it for our last one.
Yeah.
We hope you have enjoyed your time with us. We certainly have. And all the best with your exams.
Sleep.
Yes, be sure to get some good sleep. And we'll be seeing you.
Yes.
Cheers!
Bye.
Bye-bye.
See you then.